the type of critical points of a linear system. So in order to do this, let me very briefly resume what we were doing in the last 20 minutes yesterday. So if you remember, we were analyzing linear systems. Why we were starting with linear systems? We were dealing with linear systems because we proved that even if I have a non-linear system, what I can do is to expand on the around the critical point of the non-linear system, and in such a way, I can reduce my nonlinear system to a kind of linearized system. So the idea was, let's start studying the linear systems. Let's start trying to understand what kind of results I can find from the study of the linear systems, and then what I can do is try to understand if it's possible to translate those results that are found for linear systems to nonlinear systems. So a linear system is let me remind you, it's a system that can be written this way. So it's we're considering two-dimensional linear systems. So two ODEs, two state variables. These are autonomous systems. So this means that this prime is a derivative with respect to an independent variable that we assume to be t. But then the right-hand side does not depend on t. So it was something. Oops. Written in this way, y prime equal to cx plus by. Very good. We were assuming that the determinant of the matrix of coefficient of the linear system, so the determinant of the matrix which has entries given by A, B, C, and D, the determinant of this matrix here must be different from 0. I'm assuming this because this allows me to be sure that the at least here I have one critical point, which is the origin. Then what I was doing was to rewrite this this system in matrix notation. I mean, the passage in rewriting the linear system in the matrix notation, it's something which is okay. You can also jump it. The point is that if you are rewriting in the matrix notation, is easier than to analyze what are the solutions of the system. So what I was doing was to rewrite this thing here as x prime equal to a x, where this x is a vector whose components are x of t and y of t. And of course, x prime is a vector whose components are x prime and y prime of t. And finally, this A is a matrix, which is the matrix that corresponds to the matrix of the coefficient of the linear system. So this A is again the matrix that I wrote before, whose entries are A, B, C, and D, the coefficient of the linear system. So what was the advantage of writing in this way my my system? Well, the advantage was that now I can easily find a solution to this equation. Indeed, actually, this equation resembles a lot the equation for one-dimensional ODE for x prime equal to some alpha x, that yesterday we discovered to be equal to whose solution we discovered to be equal to some constant kappa k times the exponential of alpha t. Okay, so the idea is to use an ansatz similar to this solution here, also for the case of our equation written in matrix formalism, matrix notation. So the idea is to look for a solution which can be written as x vector of t equal to some b vector times the exponential of lambda t, where b and lambda are well, one vector and one scalar that should be determined by the problem. So if I'm using these ansatz, remember this is an ansatz. This means that this is a guess. So I'm assuming that the solution of this equation is something that I can write in this way. For the moment, it's just a guess. It could be also the chance that the guess is wrong. Okay, we know that this guess is good because yesterday we had seen that it's possible to find a solution with this guess. However, again, this is a kind of ansatz, an educated guess that you can do thinking about similar equations, equations that are similar to this one. Okay, so if I'm using these ansatz and I'm inserting this ansatz in my system of first-order ODEs written in matrix form, matrix notation, what do I find? Well, I found that A times B is equal to lambda B. And yesterday we commented about the fact that this is an eigenvalue problem for the matrix A. So this is the equivalent to the problem of looking for the eigenvalues of the matrix A and the corresponding eigenvectors B. So lambda are the eigenvalues and B are the eigenvectors. Why eigenvalues and eigenvectors? Basically, an eigenvector is a vector such that when I'm multiplying this vector with the multiplication row by column times the matrix A on left, so A times B, this should give me some quantity which is proportional to B. And the factor of proportionality, the factor which is outside B, is going to be the eigenvalue of the eigenvalue lambda. All right. So we are lucky enough because our problems are two-dimensional problems. So since the problem is two-dimensional, we know that this matrix A is a matrix which is a 2x2 matrix. And we know from linear algebra that a 2x2 matrix can have at most two distinct eigenvalues, lambda 1, lambda 2, and can have at most two linearly independent eigenvectors v1 and v2 corresponding to lambda 1 and lambda 2. So we are, when I say it's, we are lucky, it's because of course if you have some kind of problem or when you have n by n matrix, then this would be, you can have at most n distinct eigenvalues and n at most n linearly independent eigenvectors. Of course, this is becoming is increasing the difficulty of the problem. In this case, no. This is a 2x2 matrix. B is a vector with just one column and two rows. So it's 2x1, 2x1, and this is a scalar. So the problem is going to be relatively easy. How do you solve the eigenvalue problem? Well, in order to find the eigenvalues, what you can do is to solve the equation for the determinant of A minus lambda identity equal to 0. So if you solve this equation here, you will be able to find the eigenvalues lambdas, all the eigenvalues of the matrix A. Once that you find the eigenvalues, what you can do is to find the corresponding eigenvector. So suppose that lambda star is some specific eigenvalue of the matrix A, then A minus lambda star times identity matrix multiplied by the vector B should be equal to 0. If you solve this equation here, you will be able to find the eigenvector B corresponding to the eigenvalue lambda star. Okay? So, we have said that in 2 dimensions there can be just at most two independent, two distinct eigenvalues. So what we want to do now is try to find a kind of map, a mind map, which is telling you which kind of critical point I'm facing with by looking to the two eigenvalues lambda 1 and lambda 2, to the sign of these eigenvalues, to the fact that they are real or imaginary, to the fact that one is larger than the other or not. So let's see what does this mean. Yesterday we were considering just the first case. And the first case was the case of lambda 1 and lambda 2. Two distinct real positive eigenvalues. Now, since these are two distinct eigenvalues and the dimension of the matrix is a square matrix which is 2 by 2, this means that there will be also two linearly independent eigenvectors corresponding to these eigenvalues. So there will be an eigenvector V1 corresponding to lambda 1 and an eigenvector V2 corresponding to lambda 2. So this case is enough, because then the general solution, which is this x or t, can be written as a linear combination of the two linearly independent solutions. So one linear independent solution is B1 exponential of lambda 1 times t. The other, another solution which is linearly independent from the first one is B2 exponential lambda t. Then the general solution is going to be a linear combination of these two. So you will have some C1 and C2 constant here. I'm just writing linear combination of the linearly independent solution of the differential equation. So yesterday, the idea was to understand to what kind of critical point 0, 0 corresponds. So remember that the critical point here is 0, 0. So the idea was to understand what kind of critical point is 0, 0 when you have this kind of situation. And in order to do this, we were commenting yesterday, we were trying to analyze the general solution by killing the terms. So we say, let's consider at the beginning what happens if I'm killing this term here. So if I'm considering C2 equal to 0, I have just this term here, C1, V1 exponential of lambda t. But in the phase plane, this object here is just a line. It's a line which starts from 0, 0 and which has the which is following the direction of vector v1 or minus v1. And function that you have, well, you can have plus or minus v1 and having a line which is going up or down. Same thing happens if I'm getting this this term here, and I just have this term here. So if I put C1 equal to 0, I don't have this, I have just C2 V2 exponential lambda to t, which again is a line in the phase plane, which is parallel to V2. So in direction either plus V2 or minus V2. So since we were commenting also another thing that these objects tend to 0, to reach the critical point only for t that goes to minus infinity. So we were commenting this fact as the idea that basically these lines are lines which are departing from the critical point. So they are not really reaching the critical point because we say that orbits cannot pass through a critical point, but can approach the critical point asymptotically. So this is the case. They are approaching the critical point asymptotically for t that goes to minus infinity. Since the system is evolving in such a way that t is going forward, so t is increasing, this means that the path, the orbit, is leaving the critical point. So what does this mean? This means that if I'm just writing down, suppose that is V1 minus V1, V2 minus V2, this means that basically all these solutions are departing from the critical point which is here. So what's this critical point? This is a node, and it is unstable. So basically this tells me that anytime that I have a linear system, a system of these, so a system that I can write in this way, with eigenvalues of the matrix of the coefficient of the linear system that satisfies this kind of relation, then I'm sure that 0, 0 is an unstable node for the linear system. Questions so far? No question. The second case is a easy case because I'm considering now lambda 2 less than lambda 1 less than 0. So again, I have two distinct real eigenvalues, but now they are both negative. So basically, since they are both negative, the general solution can be again written in this way. Actually, to be more precise, what I can do is to write the exponent as minus the absolute value of lambda 1 times t, and minus absolute value lambda 2 times t. Correct? Remember, lambda 1 and lambda 2 are both negative. Question. Can you guess what would be the phase diagram in this case? So can you guess what's the nature of the critical point in 0, 0 for this linear system? Guys, some guess.
For t, which tend to plus infinite.
Yeah.
So the arrows will be in the other direction.
Which arrow?
All the 4 arrows.
Huh?
The 4 arrows.
Correct. So in this case, the solution is approaching, well, the two independent solutions are approaching the critical point 0, 0 when t goes to infinity, not to minus infinity. Right? Because the exponential of minus some quantity times infinity is going to 0, and the exponential of minus some quantity times infinity is going to 0 as well. So this basically means that as time goes by, the orbits are approaching in an infinite amount of time, are approaching the critical point. So what's the nature of the critical point? What is this critical point?
It's stable.
It's
Stable.
I'm sorry, I didn't understand.
It is not unstable.
It's not unstable. It's stable. Okay, right. It's stable, but stable what? It's a stable node. Asymptotically valid. Locally asymptotically stable. Locally asymptotically stable node. Let me also mind the fact that you have 4 classes of critical points. So you have centers when you have a critical point that is surrounded by closed orbits. Then I have nodes which can be stable or unstable, can be these or the other way around the arrows. Then I can have spirals, which again can be stable or unstable. And then I can have saddles. Saddles, which is are unstable. Okay, so the idea is to map all of these in one of these possibilities. So just looking to the eigenvalues of the matrix of this linear system, I should be able to say 0, 0 is stable or unstable node, a saddle, a center, or a stable or unstable spiral. So far, what we found is that in this case corresponds to a unstable node. This other case corresponds to a asymptotically stable node. Now let's see the other cases. Now let's consider the case in which I have lambda 1, 0, lambda 2. So I have two distinct eigenvalues, real eigenvalues, with the opposite sign. So the general solution, remember, xt, general solution, if you have two distinct eigenvalues, the general solution is going to be always of the same form. So I will always have some C1 times the eigenvector B1 corresponding to lambda 1. So since lambda 1 is negative, I can write as minus modulus of lambda 1 times t plus C2 dq exponential of lambda q t. Okay. What's this case? What about this case?
Long, about the first part, I think it's unstable, but the second part is stable. I think, I'm not sure.
Okay, so yeah, but the idea is that again, what you can do is to study the behavior to try to understand that these two parts when they are approaching the characteristic point. So when do they are approaching 0, 0. So this part is approaching 0, 0 when t goes to infinity. This part is approaching 0, 0 when t goes to minus infinity. So the idea is, broadly speaking, that we have the critical point here. Okay, so suppose that this one is the part related to, let me say, this one, to V2, the one which is parallel to the vector V2. So since this is approaching 0, 0 when t is going to minus infinity, means that as time goes by, these two lines are leaving from the critical point 0, 0. Now let me consider the first part. So C1, V1 exponential of minus lambda 1. Let me suppose that the V1 is this. So again, this is the line parallel to plus V1, and this is the line parallel to minus V1. This is approaching the critical point when t goes to infinity. So basically, as time goes by, I'm going in the direction of the critical point. Okay? So what about all the other orbits? Remember, these ones are just these paracrises. So what are all the other orbits? All the other orbits can be built out from this one. So what we can say is that the orbits are entering in following B1 and are going outside following B2. So basically any other orbit can do like this one or like this one and so forth and so on. So what is this?
A saddle.
This is a saddle. A saddle is stable or unstable?
Stable.
Why? So do you remember the definition of stable and unstable? Basically, what you have to do is to look at the orbits which are in a neighborhood of the critical point. So I can think, let me cancel that. Let me just leave few orbits. Okay, this was the critical point. So what I have to do is to look at the orbits which are in the neighbor of this, which are starting in the neighbor of this. So imagine that I'm looking to this orbit, and imagine that instead of starting here, I'm starting from this point here. Okay? So what we know is that this orbit will approach, for t that goes to infinity, the critical point. But now, let me instead consider this other branch. And instead of starting here, let me start from some point here. Okay. Okay? The orbit which is starting here, so with initial data here, are going outside, are going in this direction, are leaving the neighbor of the critical point. So what is lacking here, here we have a problem, because basically what's happening is that there are some trajectories, some paths, some orbits, which are asymptotically reaching the critical points. But not all of them, not all of the trajectories which are included in this neighborhood are approaching asymptotically the critical point. Because there are some trajectories, like for example this one, which instead are going away. So this is enough for saying that this guy here is not stable, it is unstable. Saddles are always unstable. So remember that centers are stable. Saddles are unstable. Nodes can be both stable or unstable. And spirals can be both stable or unstable. All right, in any case, this point here is a unstable center. I'm putting in parentheses just to remember that saddles are always unstable. So I'm just putting parentheses to remember that it's unstable. But if I'm saying that it's a saddle, I already should understand that this is an unstable critical point. 0, 0, for this case, is an unstable critical point. 4. Now let's consider the case in which the two eigenvalues are complex numbers. Now, let me suppose that the eigenvectors, which is again the discussion regarding eigenvalues and eigenvectors, is exactly the same of the case of real eigenvalues. So once that I define the eigenvalue, which is a complex number, I can find the corresponding eigenvectors, which will be a complex eigenvector. And in fact, let me suppose that the complex eigenvector corresponding to lambda 1 is some object that I would like to write as W plus EV. Now, let me consider then the part of the general solution which depends on this W plus IP. So the general solution, XT, will be a linear combination of this guy here plus the one which is coming from the other guy, linear independent coming from the other guy, from lambda 2. Note that in this case, lambda 2 and lambda 1 are related by the fact that these are complex conjugate one of the other. Indeed, this will be enough to define all the possible solutions which are entering in the general solution. Okay. How can I write xt? Xt is the eigenvector W plus IV times the exponential of lambda, and lambda is alpha plus beta I times t. Now what I can do, I can put on I can factorize e to the alpha t and then I have this vector W plus IB which multiplies the exponential of beta IT. So what I can do is to write the exponential of beta IT in terms of sine and cosine. So allow me to write down directly the result. So this is going to be E alpha t times W cosine beta t minus V sine beta t plus I E alpha t that multiplies W sine beta t plus V cosine beta t. The vector, the vector, the vector, and the vector. Question: do you know, no, that this thing here is equal to cosine beta t plus I sine beta t? Do you remember this, right? So I just use this expression to write the exponential of beta t in terms of sine and cosine. Ok?
Però scusi, ma si vede malissimo la seconda parte dell'equazione. Sopra. Sì, no, il vettore, quello dopo la prima parentesi chiusa, si vede praticamente nulla.
Può essere che la telecamera sta fuori.
Prof, può scrivere col nero?
Sì, adesso ci provo. se funziona. Si intuisce, si vede qualcosa? O lo...
È meglio
Sì, così
così.
meglio, prof. Molto meglio.
Ok.
Prosciutto.
Okay, in any case, here the problem is that I cannot control the focus of the camera. So it can happen that since I'm passing in front of the camera is focusing on me, and then it loses the focus on the text. That's such a what happened possibly. In any case, I'm trying to use the black one. So let me explain again what I was saying, because if you couldn't see, it was difficult. So I found the eigenvector corresponding to the eigenvalues lambda 1. And then I'm constructing the general solution of the differential equation as a function of the eigenvectors, as we have done before. Eigenvector times exponential of eigenvalues times t. And now what I'm doing, I'm using this expression, which is some standard expression to write the exponential of I beta I something, so I beta t, as cosine something plus I sine something. I hope that you know this expression. So I just rewrote this expression, this quantity here, expressing the exponential of beta t in terms of sine and cosine. So just to rearrange the terms, what I found is this expression down. This expression here. So exponential alpha t times w cosine beta t minus v sine beta t plus I e alpha t w sine beta t plus v cosine beta t. If you don't believe me, do the calculation, which is a simple algebra, and you can do that. Now, you should remember that in a complex solution, the real and imaginary part, so this part here and this part here, apart the I, are two linearly independent solutions. Actually, I can find exactly the same linearly independent solutions if I'm using lambda 2 and the corresponding eigenvectors to lambda 2. Now, since this is a two-dimensional linear system, so I can have at most two linear independent solutions. This means that I can consider just this one as my first solution, and this other one as the second linearly independent solution. So I can write in total my solution as x of t. Can you see this black?
Yes.
Yes, it's okay.
Okay. X t equal to C1 times E alpha t times W cosine beta t minus V sine beta t. No, this is not possible. Plus the second linear independent solution, which is C2 E alpha t, which multiplies W sine beta plus V cosine beta t. Can you see the solution? So what's special in this solution? What can you find of special in this solution? So let me start by looking at the quantities which are in parentheses. Okay? Look at this quantity in parentheses here, and this other quantity in parentheses here. So what can you tell me about these quantities? What do they have special? So these are periodic solutions, because these are solutions which repeat themselves every 2 pi over beta. Right? When t is equal to n 2 pi over beta, they are repeating themselves. These are periodic. This quantity is periodic. This quantity in parentheses is periodic. Right? So you can probably already see where we are going. The idea is that in principle, this kind of solution could be a solution that allows me to find some eventually closed orbit. What would be the case of closed orbit? The case of closed orbit is when just this part of the solution rules. Because in order to have a closed orbit, what I need to have is periodicity. This term, the exponential of alpha t, is spoiling the periodicity. So the only way that I have to have a periodic solution, so a closed orbit, periodic solution, the only possibility that I have is that I don't have this term e to the exponential of alpha t. These terms does not matter when alpha is equal to 0. Because if alpha is equal to 0, the exponential of alpha t is the exponential of alpha, which is 1. And this other exponential of alpha t is the exponential of 0, which is exponential of 0, which is 1 again. So if alpha is equal to 0, I have only this part of the solution, which is a periodic function. So in this case, I would have closed orbits. Okay? So if I ask you, whenever I have complex eigenvalues that are the conjugate one of the other, and alpha is equal to 0, so these are purely complex numbers. They are just the beta I part. What is the point, what is the nature, what is the type of the critical point? It's going to be a center. So alpha equal to 0 will correspond to a center. What happens if alpha is different from 0? I can have, two possibilities. Alpha less than 0 and alpha greater than 0. So what do you think that I should have in this case?
It becomes a spiral.
It becomes a spiral, yes. Can you see which of the two is going to be the stable spiral and which is going to be the unstable one? So alpha less than 0 is going to correspond to the stable spiral or the unstable one?
To the unstable one.
No, because alpha less than 0 means that here I will have something like this, which is approaching the critical point for t that goes to infinity. When I'm approaching for t that goes to infinity, I have a stable point. So alpha less than 0 will correspond to a asymptotically stable spiral. While alpha larger than 0 will correspond to an unstable spiral. If n allows me to correct. Now, what I would like before stopping for 5 minutes or 10 minutes, what I would like to show you is an example of all these things that we are seeing today. So let me, before starting with the example, do you have any questions so far? No, I can start with this. Okay, then let me consider, guys, I'm passing again to the red one. Please let me know if you cannot see because the black one are really not working. The black fence, I'm sorry. So the example, let me consider the following system. X prime equal to 3x minus 2y and y prime equal to 2x minus 2y. So first thing, let me, nobody on it. Okay. Let me find the matrix which is associated to this linear system. So I will have 3 minus 2, 2 minus 2. Just the entries of the matrix are these coefficients which are here, here, here. Okay. Now, what I have to do is to find the eigenvalues of this matrix. So what I have to do is to solve 3 minus lambda minus q, q minus q minus lambda, the determinant of this thing equal to 0. So that means this is giving me it's 3 minus lambda times minus q minus lambda. Then I have minus this times this, which is minus 4. This is equal to 2. So what do I have here? It's minus lambda times minus lambda is lambda squared. And then plus 2 lambda minus 3 lambda minus 6 plus 4 equal to 0. So it's lambda squared minus lambda minus 2 equal to 0. Which is, if I'm correct, but check if I'm wrong or not, this is lambda plus 1 times lambda minus 2. Right? Correct. So basically the two eigenvalues are lambda equal to minus 1 and lambda equal to 2. So what can we say of the critical point 0, 0?
It's a saddle.
Correct. So just looking at this, I found the eigenvalues. This is a negative eigenvalue, the other one is a positive eigenvalue, so I'm in the case 3. So for sure, 0, 0 is a unstable saddle. Just for completeness, what we can do is also try to draw the phase diagram of for this linear system. In order to do that, we should find the eigenvectors of the system. So the eigenvectors of this matrix. So let me cancel this. Let me cancel this. Just trying to remember that the two eigenvalues are minus 1 and 2. So what are the eigenvectors? The eigenvectors are those vectors that satisfy this equation. Well, here it's lambda star. So what you have to do is to take minus 1 and substitute here lambda star, and then take 2 and substitute here lambda star, and you will find the two vectors. So basically, substitute this minus 1. What I have is 3 plus 1 is 4, minus 2, 2, minus 1 times v1, v2 equals 0, 0, and this will give you a first eigenvector. The other one is 3 minus 2 is 1, minus 2, 2, minus 2 is minus 4. v1, v2 equals 0, 0. This will give you the second eigenvector. Now, this is not a linear algebra course, so let me give you directly the results. If you are solving this one, what you will find is the eigenvector 1, 2. And if you are solving this other one, you will find the eigenvector 2, 1. So the eigenvector corresponding to the eigenvalue minus 1 is 1, 2. The eigenvector corresponding to the eigenvalue 2 is 2, 1. This one corresponds to 1, 2, and this one corresponds to 2, 1. What's the general solution then? The general solution at t, it's well, all the same story, guys. This is equal to some constant c1 times the first eigenvector 1, 2 times exponential of the first eigenvalue minus 1 times t. And then the second part, which is plus c2, second eigenvector q1 times the exponential of what? Second eigenvalue q times t. So this is going to be the general solution. As you change c1 and c2, you will have all the possible orbits of the system. Now let's try to draw the phase diagram. Can I cancel the general solution? Do you mind if I cancel the general solution?
Yeah.
Can I, no? Now, what are the two vectors which are defining these paratrices? We say that these are the eigenvectors. One eigenvector was 1, 2, and the other one was 2, 1. So the two paratrices are going to be 2, 1, let's say this one, and minus 2, 1. And then I have 1, 2, and minus 1. Okay, then the eigenvector 1, 2, which corresponds to this branch, was corresponding to the eigenvalues minus 1. So we correspond eventually to orbits which are approaching the critical point. So this is going in this direction, and this is going in this direction. Instead, the eigenvalues, the eigenvector 1 corresponds to the eigenvalue 2, which basically corresponds to orbits instead that are leaving from the critical point. So the arrow is going in this direction. So now what you have to do is just to complete. So orbits in this sector will go like this. Orbits in this sector will go like this. Orbits here will go this way, and orbits in this sector here will go like this. Here it is your sample. Any question?
Professor, I'm sorry. I understand all of the things that you said, but about one point, I can't understand the diagram that they are approach or not to the critical point. I can't draw a paragraph. I don't know.
Okay, okay. So, in order to see if they are approaching or leaving the critical point, what I have to do is to see what is the behavior of the solution for t that goes to minus infinity or plus infinity. If I have the general solution which has a factor which looks like this exponential of alpha t, where alpha is a positive number. Okay, let me start from the assumption that alpha is a positive number. Okay, when is this expression true? So what shall I put here? Here I'm looking limit of the exponential of alpha t. I want it to be 0.
Minus infinity.
So this is minus infinity. What instead is alpha less than 0? What instead these are the things? Well, as you can probably imagine, in this case,
To positive infinity.
very good. Now, imagine that this parameter t is telling you what's the arrow of your time. Okay? Suppose that this t is your time. The fact that I'm approaching 0 for t that goes to infinity means that I'm approaching 0 in the future. Okay? I'm going towards 0. It's like I'm going towards 0. So if I'm going towards 0 in my diagram, if this is the critical point, I will have something like this. Because I'm going towards 0. Okay? Now instead, suppose that this is the other diagram. The fact that I'm approaching 0 for t that goes to minus infinity means that I can approach in the very far past the 0. So since I'm going toward the future, I want to see where I'm going when time is passing. So I want to see where I'm going in the future. So if minus infinity is the past, in the future, I'm going in the other direction. So this is gonna be like that. The arrow will point toward infinity, toward outside, leading to the critical point. Can you see the impact?
Yes, professor.
So if there is no other question, let me take 5 minutes of break, and then we will come back, okay? So let me add also some details regarding the exam because I was thinking about one detail regarding the written exam and then the oral exam. So the idea is that well, my idea was the following. My idea was you do the written exam, and then the written exam uh, is fine for the entire session. So what I mean is that if you're doing the written exam, for example, in December, then this will be useful for doing the oral exam for the entire session, for the entire winter session. So you can do the oral exam also in the February, you know, at the end of January. When is it start? When is ending the winter session? January, February? No.
At the end of February.
At the end of
February.
At the end of February. Okay, that's fine. So if you're doing the written exam, you can do the oral at the end of February if you prefer. In such a way that you have more time to prepare yourself. That's the idea. But once that you do the oral exam, you will consume your written exam. I mean, if you're doing the oral exam and you are not passing the oral exam, you have to repeat also the written exam. Okay? I don't know if I was clear or not. I can repeat if you want. So passing the written exam give you the right to do once the oral exam. That's the resume, the summary.
Professor, the written exam is similar to oral exam or not? I mean, you. I don't have your. I can't hear you.
I heard my voice back. So, but yeah, basically the idea is that in the written exam you will find some kind of exercises like those ones that I'm giving you during the weeks. Like you remember last week we had a couple of exercises. Okay, this week at the end of the lecture I will give you some other exercises like three or four of them. The idea of these exercises is that you are trying to do this by yourself at home. Okay, I decided that I will post the solutions of these exercises in such a way that you can check if the exercise was well done or not. But the idea is that there are going to be exercises similar to those ones. And then in the oral part of the exam, I will ask questions about the errors that you did in the written part, or eventually some theoretical question. So, for example, I can ask if there is an exercise where I'm asking you to find the nature of the critical point, and you find that the critical point is, I don't know, a center, then I could ask, okay, that's fine. What are the other types of critical points that you can have? How can you say that the critical point is a saddle rather than a unstable spiral? Things like this.
Okay, thank you. Thank you so much.
So we start with the second part now. Yeah. Yeah. So in the second part, we are going back to nonlinear systems. Yeah. So if you remember, my original problem was the analysis of a completely generic system. It's a nonlinear case. X prime equal to P of X and Y, and Y prime equal to Q of X and Y. So what we proved is that it's possible to linearize around a critical point X naught Y naught the nonlinear system. So what I will end up is some linear system that I can write it this way, where the matrix A is a matrix that we call the Jacobian of the linearization. So it's a matrix here which has the partial derivative of P with respect to X calculated in X naught Y naught. Then I have Py calculated in X naught Y naught. Then I have Qx X naught Y naught and Qy X naught Y naught. And this is 5. So the result that I'm going to give you now, I'm not going to prove the theorem, but something that you have to know, because otherwise you cannot apply then the idea. So what I'm trying to do now is I would like to predict what is the nature, what is the type of the critical point X naught Y naught of the nonlinear system, this gentleman here, by looking the nature of the critical point in the linear system. So I have the linear system. We have studied before, last hour, we have studied the nature of the critical point of a system like this one. Now, what can I say about the nature of the critical point of a nonlinear system that generated this linear system? This is the main question. And the answer to this question is given by a theorem by Poincaré, which has the following. So suppose that X naught Y naught is a critical point for the nonlinear system. So let X naught Y naught be a critical point for the nonlinear system. And suppose that this Jacobian here, this matrix here, is not singular. So suppose that the determinant of A is different from 0. Then the critical point x naught, y naught will be of the same nature, of the same kind, of the critical point 0, 0 of the linear system. So the critical point here is 0, 0. In the following cases. So, first case. If the eigenvalues of A are both real and have the same sign. So, what's this case? Real eigenvalues, real positive distinct eigenvalues. What is this? It's a node. So, the idea is that I'm starting with the nonlinear system. The nonlinear system has a critical point in x naught, y naught. I calculate the linear system associated with this one. So the linear system around this x naught, y naught. The critical point of the linear system is 0, 0. Let me study the matrix A. The matrix A has eigenvalues which are both real and with the same sign. So I know from the analysis that I've done before that then 0, 0 is a node of the linear system. The Poincaré's theorem tells me that x naught, y naught will be a node of the nonlinear system. So eigenvalues, second case, eigenvalues of A are both real and with opposite sign. In this case, as you probably don't remember because we have said this a few minutes ago, but this is the case of Isaac. So again, what does this mean? That 0, 0, the critical point of the linear system, in this case, is a subtle. But then, Poincaré's theorem tells me that x naught, y naught is a subtle for the nonlinear system. Third case. So the eigenvalues, blah blah blah, eigenvalues of A are complex, but not purely imaginary. This case, the cases which are complex but not purely imaginary, we are seeing that correspond to spirals. Okay? So a spiral for the linear system will correspond to a spiral for the nonlinear system. fair enough. The point is that I cannot say anything for the center. So Poincaré's theorem does not tell me anything for the center. Well, actually, a center would correspond either to a center or to a spiral, but I cannot tell anything before analyzing the nonlinear system itself. So, resuming, summary, Poincaré's theorem tells me that if x naught y naught is a critical point for the nonlinear system, and if the Jacobian here is non-singular, the Jacobian of the linearization is non-singular, so if the determinant of A is different from 0, this means that A is non-singular, then a node for the linear system corresponds to a node for the non-linear system. A subnode for the linear system corresponds to a subnode for the non-linear system. A spiral for the linear system corresponds to a spiral for the non-linear system. Center, I cannot say anything. Well, it could be either a center or a spiral for the non-linear system. So for example, let me consider the following non-linear system. X prime equal to qx plus 3y plus xy, and y prime equal to minus x plus y minus q x y to the power 3. Okay. Now, the first thing that you have to do is to find the critical points for the nonlinear system. And in order to find the critical point, the procedure is always the same. So what I have to do is to put equal to 0 the derivatives, x prime and y prime. And I have to solve this system. So I have to solve 2x plus 3y plus xy equal to 0, and minus x plus y minus qxy cubed equal to 0. Okay, you will have a number of a certain number of critical points. I'm interested. There is just one. In this case, there is just one real critical point. The other ones are imaginary solutions that, in this case, can be discarded. So the critical point for the nonlinear system is 0, 0. A real critical point for this system. Indeed, if you put x equal to 0 and y equal to 0, you soon realize that this thing is equal to 0 and this thing is equal to 0. So surely 0, 0 is a critical point for the nonlinear system. Now, what's the nature of this point? In order to answer, we have to linearize the system. So let's linearize. Linearization. Do you remember what's the linearization? So, linearization, I'm expanding x as x naught plus u and y as y naught plus b. In my case, x naught and y naught are 0 and 0. So I'm expanding, I'm taking x equal to u and y equal to b. So what happens here? I will have x prime is going to be u prime equal. Do you remember what happened here on the right hand side? What I have to do is to Taylor expand p in x naught y naught. So this is going to be equal to p of x naught y naught plus the derivative of p in x, evaluating x naught y naught times u plus the derivative of p in y, evaluating x naught y naught times b. Now again, x naught y naught are 0, 0. And p of 0, 0 is this quantity here, 2x plus 3y plus xy, evaluated in 0, 0, which is 0, 0, 0. This guy here is 0. Now, the derivative of p with respect to x. What's the derivative of p with respect to x? Is the derivative of this quantity with respect to x. So it's 2 plus y. And I have to evaluate 2 plus y in the critical point, which is 0, 0. So y is equal to 0. So 2 plus y is 2 plus 0, which gives me 2. So this term here can be written as 2 times u. And then I have py, the derivative, the partial derivative of p with respect to y, which gives me 3 plus x. Again, I have to evaluate this derivative in 0, 0. So x is going to be equal to 0. They have 3. So this guy here is 3b. So I can rewrite all these things here as 2u plus 3b. I have to do the same with the second equation, the equation for y prime. So y prime is going to be b prime equal the derivative of q, so of this function here, with respect to x, evaluated in 0, 0. So the derivative of this with respect to x is minus 1 minus 2y cubed. But I'm evaluating in 0, 0. So when y is equal to 0, I just have minus 1. And finally, I have to evaluate the derivative of this with respect to y. So this gives me 1 and minus 2x times 3y squared. But I have to evaluate this in 0, 0, so this thing is equal to 0. I just have 1 plus 1 times p. Right. Let me do this. So the linearized system can be written in this way, as u prime equal to 2u plus 3b, and b prime equal to minus u plus b. What's the Jacobian? Jacobian means now the matrix A, this guy here. So it's going to be the matrix of the coefficients of the linearized system. So it's 2, 3, minus 1, 1. Now, what I have to do is finally to find the eigenvalues of of this matrix. So the eigenvalues of the matrix are given by the determinant of 2 minus lambda, 3 minus 1, 1 minus lambda. So determinant equal to 0 will give me the two values of lambda, which are the eigenvalues of the matrix. Now, what's this determinant? This determinant is equal to 2 minus lambda times 1 minus lambda minus 3, which is equal to lambda squared minus 3 lambda plus 5. Now, if I'm correct, I hope to be correct, but please check if I'm correct or not. The two roots of this equation of lambda squared minus 3 lambda plus 5 equal to 0, the two roots are 3 alpha plus or minus I times square root of 11 alpha. So what does this tells me? Here, what I found is that the linearized system has two complex eigenvalues, which are one the complex conjugate of the other, two complex eigenvalues whose real part is larger than 0, these 3 alphas. So what does this mean? This means that the critical point for the linearized system, 0, 0, for the linearized system, is a spiral and is an unstable spiral. What do we know? That for spiral, we can apply the Poincaré theorem. So what we can say is that 0, 0 will be for the non-linear system a spiral as well. So 0, 0 is a spiral for the linear system for this reason, but Poincaré theorem tells me that 0, 0 is a spiral also for the non-linear system. Questions? No question. Okay. Then let's see an application, a problem. So let me consider let me guess. And then let me see. I will consider a particle of mass 1, so a point particle with mass equal to 1, which moves just on the x-axis. and subject to a force, which is a conservative force, or equal to 3x squared minus 1. So Newtonian dynamics, you know that I should have m this squared x infinity squared equal to the force. It's just F equal to m times a, no? In this case, the force depends on x. It's a conservative force, which is depending on the position. So this guy here is 3x squared minus 1. On this other side, we say that the mass is equal to 1. So this guy, let me write this guy as x prime prime. So it's x prime prime equal to 3x squared minus 1. So we have seen in 2 weeks ago that it's possible to use these kind of equations to a system of first order ordinary differential equations. So what I can do is to define the velocity y, which is equal to x prime, so x prime equal to y, and then y prime is x prime prime, so this guy here is equal to 3x squared minus 1. So what I did is to obtain a nonlinear system of first order ordinary differential equations from this equation here. Now I can analyze this system in 2 different ways, and that's what actually what I will do in order to show you the power of the linear analysis of this system. So the first way you can analyze the system is to consider the fact that it is a mechanical system with the conservative force. So the fact that they have a conservative force means that there is a potential V which is equal to minus the integral of the force. This is minus the integral of 3x squared minus 1, which gives me minus x cubed minus x cubed, and then I have plus x. Then since the force is conservative, I can apply the energy conservation principle. So the energy is going to be equal to the kinetic energy of the system, which is 1/2 times m, which is 1, times m of m is 1, times the velocity squared. The velocity, remember that is x prime, so it's y squared, and f is 1. So 1/2 y squared plus the potential, which is x minus x cubed. From here, E, the energy, is some number. So you are saying that your energy has an energy, your system has an energy of 10. So what you are doing is to define an energy level, and you have to solve this equation for that energy level with E equal to 10. What you will find is some expression for y. In this case, y will be equal to plus minus square root of q times the square root of e plus x cubed minus x. The equilibria of the system are the points where the point mass is still, does not move. So are those points where the velocity is equal to 0 and the force which is acting on the point is also equal to 0. So this means that there are two equilibria. The equilibria are 1 over square root of 3, 0, and minus 1 over square root of 3, 0. So now what I can do is to plot these functions here when I'm changing the energy E. So I'm fixing E and I'm drawing the curves that I get from this function. And what I find is something like this. So this and these are the two equilibria. And then I have this. This. Now this complicated structure that looks like a fish is exactly what you obtain just plotting this object here. I can understand that this is something difficult to visualize. You can take any software, mathematical software, and give it to feed with these functions, and then evaluating for different energies. What you will find is a diagram with like this one. Okay. Now, in order clearly to find the diagram, it's going to be a bit complicated because you have to solve these things and again, if you do not have a computer, it's going to be a bit complicated to find out this kind of behavior. What you can do instead is to analyze the system, the nonlinear system, using the linearization analysis. So, in order for doing that, I would like to cancel something. Can I cancel this part?
Yes.
Now, so what I have to do is, first of all, I have my nonlinear system. First of all, let's find what are the critical points of the nonlinear system. So the critical points of the nonlinear systems are going to be the solution of x prime equal to 0 and y prime equal to 0. That is, y equal to 0 and 3x squared minus 1 equal to 0. And the two solutions are 1 over square root of 3, 0, and minus 1 over square root of 3, 0. So the critical point that I found are exactly the same that I found with the mechanical analysis of the system. Now what I have to do is to linearize this system around the two critical points. So I'm starting by linearizing this guy around minus 1 square root of 3, 0. So this is u prime equal to, you remember, is the function on the right hand side evaluated in the critical point, but the right hand side is just y evaluated here in 0, which gives me 0. Here is 0. Yeah. And then I have the derivative of this function with respect to x, which is 0. And then the derivative of this function with respect to y, which is 1, evaluated in the critical point. Still 1. Here on the right hand side, I have u prime equal to, sorry, on the right hand side I have b. Okay, because well, it was too quick. So this is what I'm calculating. So this thing, the first part is 0, this part is 1, so it's 1 times b. On the right hand side, it's going to be just b. Now what I have to do is to calculate b prime. So I have to linearize this equation here. So y prime is going to be just b prime equal to what? Again, is this function evaluating the critical point, but this function evaluating the critical point is going to be equal to 0 because the critical point is the one which makes vanishing the right hand side of this system. Then I have the derivative of the function with respect to x evaluated in minus 1 over square root of 3, 0 times u. And then the derivative of the function with respect to y evaluated in minus 1 square root of 3, 0 times b. And let's see what is giving this. So this function does not contain y. So surely this term here, the derivative with respect to y, disappears. Now this term here, the derivative with respect to x is from here, it's going to be 6x. But I have to evaluate this 6x in the critical point, which is minus 1 square root of 3, 0. So x is minus 1 square root of 3. Which I can write as minus 6 square root of 3 divided by 3. So as minus 2 square root of 3. So the right hand side reads minus 2 square root of 3 times u. Okay, fantastic. So what is the Jacobian of this linearization, of this transformation? This is what is this? 0, 1, minus 2 square root of 3, 0. So what I have to do is to find the eigenvalues of this guy here. So I have to calculate the determinant, lambda, lambda minus lambda, the determinant of this object here. And put this determinant equal to 0. So the determinant is lambda squared minus 2 square root of 3 equal to 0. Which means lambda squared plus 2 square root of 3 equal to 0. Which means that the solution are lambda equal to plus minus I times the derivative of the square root of 2 square root of 3. So what does this tell me? This tells me that the two eigenvalues are purely imaginary numbers, and eigenvalues with that are purely imaginary numbers corresponds for the linear system to a center. What can we tell for the nonlinear system? Well, this is the Poincare theorem. The Poincare theorem does not tell me anything concrete in this case, but what I can tell, what I can say is that surely the point, the critical point -1 over square root of 3, 0, either is a center or a spiral. And indeed, is exactly what I found here, because this is the point -1 over square root of 3, 0, which is a center. So is this option here. Now let's linearize the nonlinear system about the this other critical point, around 1 over square root of 3, 0. So the procedure is always the same. Let me cancel this. Here I should have px times u plus py times v. Px is the derivative of this function with respect to x, which is 0. Py is the derivative of this with respect to y, which is 1, evaluated in this critical point is 1. So here on the right hand side, I have 1 times v, which is v. What about the second equation? The second equation, here on the right hand side, I have the derivative of q with respect to x times u plus the derivative of q with respect to y times v. When I'm saying q, because I'm thinking about the notation that we were using yesterday. So q is this function on the right hand side of this equation. So derivative with respect to y of this thing here is equal to 0 because does not appear y, and I can cancel this thing. The derivative of q, the derivative of this with respect to x is again 6x. Now I have to evaluate this 6x in the critical point 1 over square root of 3, 0. So this guy is going to be 6 over square root of 3, and I can multiply by and divide by square root of 3. This is 3. Simplify this, and this is 2 square root of 3. this is q square root of 3 times u. Now, what is the Jacobian of the second transformation? The Jacobian is given by 0, 1, 2 square root of 3, 0. And what I have to do now is to calculate the eigenvalues of this matrix. So for calculating the eigenvalues, I have to calculate the determinant of this object and solving for the determinant equal to 0. But the determinant of this object is lambda squared minus q square root of 3 equal to 0. So what are the two roots? The roots are lambda equal to plus minus square root of q square root of 3. So look at that. These are two distinct eigenvalues. They are both real. One is negative and the other one is positive. So I know that for the linear system, this corresponds to a saddle. And Poincaré theorem tells me that a saddle in the linearized system corresponds to a saddle in the nonlinear system, which is actually exactly what you find in the direct mechanical analysis of the system. This point here, which is the critical point 1 over square root of 3, 0, is behaves as a sample. Any question? No question?
So,
Yeah. Okay, then let me move on with another example. This is a nice example, which is the Roth-Caboterra model. So the Roth-Caboterra model, probably you know under another name, which is the prey-predator model. It's basically a model that is describing the interaction between a prey and the predator. So the idea is to use a kind of modification of the logistic equation to take into account the interactions between prey and predator. So suppose that X is my prey and Y is my predator. If there is no interaction, the prey, imagine that they are rabbits, okay? So the prey increase in number, and we can describe this with, we have seen this last time, well, a couple of times ago, with the terms going like R times X, where this is some rate of the, which measures the increasing population of rabbits. And then we have foxes. Foxes do not eat grass, so they can just eat rabbits. And if there are no rabbits, the population of foxes is just reducing, is going down. So there is a similar term to this one, which is minus, what's the number? Y. So the number of rabbits without interaction, the number of rabbits is increasing like this, the number of foxes is decreasing like that. Now, we remember that when we were commenting the logistic equation, we were saying that it is reasonable to put the second term here, which was going like x squared, because it was taking into account possible interactions of members of the population. So any member of the population can interact with the other members of the population. So here you will have some excellent that is going like x squared, population squared. Now what I want to do here instead is to put some interaction that you can have between foxes and rabbits. So here I will put some terms that put in contact foxes and rabbits. If a fox meets a rabbit, the fox eats the rabbit. So the population of rabbits will decrease of some amount that depends on the possible encounterings between foxes and rabbits. So instead of having here a term that is going like x squared, here I have a term that is going like x times y. On the other side, here for foxes, I will add another term that is again a term that takes into account that if foxes are meeting rabbits and eating rabbits, they can survive. So I will have some term with some other parameter b that is like this one. So this is the lotta for terra model. Now let me rewrite the expression which are on the right hand side. The first one I can put outside an x, so it's x times r minus a y. In the second one I can put outside a y, and I have y times minus n plus bx. Now, what I have to do is to find the critical point, the equilibrium of the system. The critical point of the system are given by this thing equal to 0 and this other thing equal to 0. Now, there are two possible real solutions. One solution is 0, 0. And the other solution is m over b r over a. So basically, this solution 0, 0, corresponds to the extinction of foxes and rabbits. the solution MBRA corresponds to a solution where rabbits and foxes arrive to some equilibrium and live in equilibrium. Now let's see what happens if I'm linearizing around 0, 0 or around this other point. So if I'm linearizing around 0, 0, what I found, I will write directly the results. I'm not doing calculation at the time. Is U prime equal to RU and B prime equal to minus MB. With the Jacobian transformation of the linearization given by R0, 0 minus N. You can already read out the eigenvalues from the form of this matrix, because this is a diagonal matrix, so the eigenvalues are going to be exactly the values, the entries that you find on the diagonal of the matrix. The two eigenvalues for this matrix are R and minus N. So this corresponds to have two distinct eigenvalues, which are both real. One is positive and the second one is negative. And we know that this corresponds to a saddle. This is in a stable equilibrium. And that's a saddle. We know that for saddle, Poincare theorem tells me that a saddle in the linearized system corresponds to a saddle in the nonlinear system. So 0, 0 will be a saddle, an unstable point for the nonlinear system of the Lotka-Volterra model. 0, 0 is saddle. Now let's linearize around M over B R over A. Again, let me write directly the results of the linearization. Which is minus A M over B times B and B R over A times U. Which basically means that the Jacobian of this linearization transformation is 0 minus A M over B, B R over A, D. So I have to find the eigenvalues of this guy here. So what are the eigenvalues? I can find the eigenvalues solving the eigenvalues equation, which is the determinant of this thing equal to 0. What's the determinant of this matrix? It's lambda squared minus parentheses minus a m over b times b r over a. By this is equal to 0. But then I have lambda squared plus mr equal to 0, which basically tells me that the eigenvalues in solution are plus minus I m times r. So this case here is the case of two complex eigenvalues which are purely imaginary numbers. So for the linear system, this corresponds to a center. For the nonlinear system, well, Poincaré theorem cannot tell me anything conclusive, but I know that to a center will correspond to either a center or a spiral in the nonlinear world. So this this point here, this critical point here, will be either a spiral or a center. Actually, you can calculate this directly. Because I can do the following. I can look at these equations. I can divide the second equation by the first equation, so I can calculate y prime divided by x prime is equal to y times minus m plus bx divided by x times r minus a y. But y prime divided x prime is dy in the t divided by dx in the t, which is equal to dy in dx. This is a simple differential equation that you can integrate by.
Sorry.
Yes.
Sorry, Prof. Why we are doing this?
Because I want to check this second statement about the critical point m over b r over a. So if I ask
to
you,
understand, sorry.
If I ask you, tell me what are the critical points of this nonlinear system looking to the corresponding linear system, you would answer in this way. 0, 0 is a saddle, and this other one is either a spiral or a center. Okay? Now what I'm doing is some extra calculation for checking if this thing here is true. Okay? In particular, I'm just thinking about the second critical point, this critical point. So if I'm doing this procedure, I can integrate this stuff, and what I will obtain is an expression which is no. So it's r times log y minus ay equal to bx minus m log x plus some constant. So this is something that you can obtain. It's not difficult. You can try. It's just by separation of variables. This is an easy differential equation that you can integrate by separation of variables. Okay. So this will be a solution. This is basically the expression of your orbits. This is a complicated expression of the orbits because you cannot solve any of the two variable x or y with respect to the other one. Try to do that. Try to find y as a function of x, or if you want to try to find x as a function of y. This is actually complicated. You can try to plot the solution, and here also, let me suggest that try to plot the solutions using some software. I don't know which kind of software you use, Mathematica, MATLAB, Maple, Python. It's plenty of possibility out there, and most of them you should pay, but I know that the university is giving you the possibility to use MATLAB for free. Python is also for free. You can go and download Python and learn programming in Python. So you can plot this function directly with the software, and what you will find is this kind of orbits. So basically, these orbits corresponds to different values of this constant here. And here in the middle, there is a critical point, and this critical point is, what a surprise, exactly this one, m over v, r over a. So the critical point for the non-trivial critical point of the Lotka-Volterra model is a center, which is something that I would have expected by the non-linear analysis, even if it was not a conclusive analysis. Any questions? One. There is just last thing that I want to tell you today.
Professor, I'm sorry. How we can solve this equation with MATLAB? I mean, what can I search in the internet about this equation?
Okay, look, I'm not a user of MATLAB, frankly speaking. You should look to some function that allows you to draw implicit functions. In Mathematica, for example, you can use some function which is called, I can tell you, I don't remember the, well, in Mathematica, you can use a counter plot, a function which is called counter plot. Contour plot. I don't know, frankly speaking, in MATLAB, what is the equivalent command that you can give for plotting these things.
Thank you.
Basically the same. If you know the command that allows you to plot a circle, that will be the same command. If you're able to plot the circumference, then it will be the same command also to plot this kind of of functions.
Okay, thank you so much.
Now, last thing I want to talk about today is bifurcation. So what we have seen is how to deal with nonlinear systems, which are of the form x prime equal to p x y and y prime equal to q x y. What I want to do now instead is to see what happens if I'm including here another parameter, mu. Note this mu is not the independent variable, okay? The dependent variable here is t. So this system is still an autonomous system. But what I want to see is what happens when I'm changing this mu. Because what I want to see is what happens to the critical points of this system when I'm changing mu. The idea is that when I change mu, there are some points which which are of a particular kind, which have some characteristics that are changing to other characteristics as far as this mu increase or decrease. So I'll give you a very simple example to understand the core of the problem. So for example, let's see what happens to the system x prime equal to x plus mu y and y prime equal to x minus y. Okay? This is already here. I don't have to do any linearization. So I can look directly to the matrix of the coefficients of this linear system. This matrix is 1, mu, 1, minus 1. I want to find the eigenvalues because I want to understand what are the what is the nature of the critical point for this system. By the way, it is a linear system, so should have the with the non-singular matrix. This should have at least 0, 0 as a critical point. So I want to understand 0, 0, what kind of critical point is for this system. Let's study, as we have done now since 2 hours and a half, let's study the eigenvalue problem for this matrix. So I have 1 minus lambda, mu, 1, and minus 1 minus lambda, and I have calculated the determinant of this, and so the determinant of this thing equal to 0. Right now, this is 1 minus lambda times, well, there is a minus in front and 1 plus lambda minus mu equal to 0. So this is minus 1 minus lambda squared minus mu equal to 0. And I can write like lambda squared minus parentheses 1 plus mu equal to 0, whose solutions are lambda equal to plus minus square root of 1 plus mu. Now, observe that I have basically 3 possibilities. And the possibility that mu is larger than minus 1. Mu equal to minus 1 and mu less than minus 1. Now, if mu is larger than minus 1, here I have the square root of a positive number, which is going to be some real number. So the eigenvalues will be two real distinct eigenvalues with opposite signs, which basically means that 0, 0 is going to be a sample. For mu less than -1, then this term, which is under the square root, is going to be a negative number. So the square root of a negative number is an imaginary number. For lambda, the eigenvalues, the two eigenvalues lambda, are going to be two purely imaginary numbers. So since I have two purely imaginary numbers, I know that this guy here corresponds to a center. Mu equal to -1 is a particularly different case. What I can do is to rewrite the system considering a mu equal to -1. So this will be x prime equal to x minus y and y prime equal to x minus y. I have to consider the equilibrium, the critical points of the system. The critical points are given by these things equal to 0, this thing equal to 0. But the solution of this is x equal to y. It's not just one point, it's a line. So for mu equal to -1, I would have a line of equilibrium point, line of critical points. So note also another thing, that the saddle is always unstable. In the center, it's always stable. So what's going on here? I have this system which has a further parameter, which is mu, that I want to change. Now imagine that I'm starting with the mu, which is very large, it's 100. So I'm starting from a situation in which the critical point is 0, 0 is a saddle, it's an unstable critical point, it's a saddle. But then I'm reducing mu is becoming smaller and smaller, and then eventually it's becoming less than -1. Then 0, 0 change its nature. It will not be anymore an unstable saddle, but will be a stable center. So we say that the value of mu at which you switch from one nature to the another, so from a stable saddle to center to stable center, or vice versa. So this mu equal to -1 is a bifurcation.
I'm sorry, Professor, I can't read something that you wrote in front of the mu equals -1. Yes, yes.
So here
The middle one.
the middle one is mu equal to -1 corresponds to a line of equilibrium. It's not just one point, because it's a line. It's x equal to y. All these points will be equilibrium for mu equal to -1.
Yes, thank you.
I'm going to give you another example, the very last example for the case of bifurcation. Okay? So I'm going to consider this system is a bit ridiculous system. Instead, now I want to consider this other system. Minus y minus x times x squared plus y squared minus mu, and x minus y times x squared plus y squared minus mu. So what you can prove is that 0, 0 is a critical point for this system. Well, that's easy. Just put 0, 0 here inside, and you will discover that these two terms will be zeros. So indeed, 0, 0 is a critical point for this. If you linearize this nonlinear system around this critical point 0, 0, the linear version of the system that you find is something like that. U prime equal to mu u minus b, and b prime equal to u plus mu times b. What's the matrix? Mu minus 1, 1, mu. What's the eigenvalues? They're given from this. Determinant of the matrix equal to 0. You can do the calculation. What you find is that lambda has the two values of lambda are mu plus minus I. So what are here the three possible cases? I can have mu equal to 0, mu larger than 0, and mu smaller than 0. If mu is equal to 0, then it means that I have lambda equal to plus minus I, which means that I have two purely imaginary eigenvalues. So the point is surely a center, which is a stable critical point. If mu is larger than 0, then I have the two eigenvalues are two complex numbers with the real part that is larger than 0. So the real part of lambda is larger than 0. Which basically means that here we have a spiral which is unstable. There is a last case, which is a case in which mu is less than 0, which corresponds to have two eigenvalues with the real part less than 0. Again, it corresponds to spiral. In this case, stable spiral. So what we proved is that a spiral corresponds to a spiral in the linearized world will correspond to a spiral in the non-linear world. So basically, in this case, for mu greater than 0, I would have a 0, 0, which is a spiral, an unstable spiral. For mu less than 0, I will have 0, 0 to be a stable spiral. And this will be true both in the linear world and in the non-linear world. So this means that in mu equal to 0, there is a change in the stability, of the critical point. So again, mu equal to 0 will be a bifurcation for the non-linear system, or also for the linear system. Questions? Comments? Desires? Ideas? None. Just want to to give up with them. Okay, guys. It's enough for today. We'll post my notes in tomorrow. On the notes, in the last page, you will also find a couple of, well, 1, 2, 3, 4, 4 problems that I invite you to solve in order to have a bit of gym, mathematical gym on these aspects. Well, if you have any doubts, I invite you to contact me by